My name is Paola Rebusco. I am a postdoctoral fellow here at MIT. I'm a theoretical astrophysicist. This means that I spend my day trying to understand the behavior of matter in the vicinity of black holes, neutron stars, and clusters of galaxies. However, today I will tell you about something that is much more common and present in everyday life, and I'm sure you are familiar with. We will talk about the mysteries of soap bubbles. Whoop, it's exploded. Soap bubbles have attracted the attention of many painters all over the years. Painters such as Bartolomé Murillo, Jan Steen, Jean-Simeon Chardin, Edouard Manet, Rembrandt, and many others. You can see now a couple of examples. This is a famous painting by Chardin, and this one is by Edouard Manet. And you can notice how the painters really got to catch the details of the soap bubbles themselves. Soap bubbles are really fun and beautiful, but they're also complex and mysterious. Did you ever wonder, for example, why soap bubbles are spherical? And where does the color of soap bubbles come from? Why do we have to add soap to the water in order to get some bubbles? Today, and in the next module, we will try to answer these questions and much more. This first module focuses on the shape of soap bubbles, and the next one will explore the colors. For now, you can stop the video and try the first activity in class. You will be exploring different solutions, different recipes to make soap bubbles. See you soon. Welcome back. So, it's not a big surprise. You found out that in order to be able to make soap bubbles and soap films, you actually had to add soap to the water. Is it the same in microgravity? Well, you can try to discuss this in the classroom and then watch this video that was taken by an astronaut named Don Petit at the International Space Station.
This subject is working with stretched thin films of water, and what we have here is a baggie which makes a nice two-dimensional beaker for use in zero gravity. And here I'm filling a small Ziploc up with water, and it makes a real handy way to handle an open container of water, and it's basically two-dimensional. And there you see a little wire loop that I made from stainless steel safety wire from the clamp and bracket kit. And that's just our deionized water that comes from the SRVK. And so I'm going to stick this wire loop in the baggie, and there's no soap or anything in that water. It's just our pure drinking water. And you pull the wire loop out from the baggie, which makes that two-dimensional beaker, and lo and behold, you have a stretched thin film of nothing but water hanging onto your loop. And so it's like a soap film, only it's just water. And we've never seen anything like this before, where you can make a thin film of pure water, and it has some rather unusual properties, which you'll see here. It's thin. It's about half the thickness of the wire, and that's a 25 thousandths wire, so that puts the film at about 300 microns thick. It's thick enough that it doesn't exhibit the interference colors that soap bubble films do. Soap bubble films are a lot thinner, but it's quite a tenacious film, as you can see there. It kind of acts like a rubber film or a drum head. You can sit there and shake the loop around, and you can collect these fairly large lenses of water induced from the flow, and it just sits there and hangs onto the film.
Hello again. In order to understand what is going on at the space station, we first have to introduce the concept of surface tension. So let's consider a liquid. Here in this bowl, I just have some plain water. In the liquid, there is some part that's in the bulk and another part that stays on the surface. We can look at the sketch here. This is a sketch of the forces between molecules on the surface and in the bulk of a fluid. Each dot represents a water molecule and the arrows represent the forces. These are electrical forces that keep the molecules close to each other. Water molecules tend to stick to each other, to stay closer. When we consider a molecule in the bulk, it is surrounded by molecules of the same type. It swims in a bath of molecules of the same type. So it feels the same force, the same attraction in every possible direction. As a consequence, the net force that it will feel is zero. Nothing happens. At the surface, this is different. As you can see, at the surface, the molecules still feel the attraction towards the bulk and towards their neighbors, but they feel much less attraction toward the air. That's much less dense, 1,000 times less. As a consequence, the molecules at the surface feel a net force that is directed toward the bulk. And what it tries to do, it tries to reduce the area of the surface itself, because it wants to have the water molecules as close as possible. And as a result, the surface is a little bit elastic, like the rubber of a balloon. There is a scientist named Charles Boyce who wrote a beautiful book about soap bubbles, and he actually called this effect on the surface of water the skin of water. The skin of water, it's the thing that allows some insects to be able to walk on the water. And as you will see, it's strong enough to support a clip without letting it sink. Here, I have a paper clip and a piece of paper towel that I'm using just to do things gently. I first put the paper towel in the plain water, then I place the paper clip and I try to get rid of the paper towel. Here it is. And as you can see, the skin of the water supports the clip. It doesn't let it sink. Isn't this amazing? Now, what happens if I add some soap in the solution? Ready? I'm going to do it now. I do it here so it doesn't perturb the clip itself. I add just a single drop. And as you can see, the clip sinked immediately. Why is this happening? We first have to give a look at the structure of soap molecules. You can see again from this sketch that soap molecules look a little bit like tadpoles. They have a head and a tail. The head is attracted by the water, while the tail is repelled by the water. This is why the head is called hydrophilic. It's from the Greek, from hydro, that means water, and philos, that means to like. The tail is hydrophobic, from hydro, that means water, and phobos, that means fear. The tail are fearful of water. Let's go back to our bowl with the water and the paper clip. Here I made a sketch of the bowl, the water, and the clip. When there is no soap, the skin of the water is strong enough to support the clip. However, when we add the soap molecules tend to stick their head towards the water because they like the water. They are hydrophilous, and they try to point the tail as much as possible away from the water. As a result, they concentrate on the surface, and all the water molecules on the surface cannot stay so close to each other because in between there are soap molecules. The result is that the skin of the water weakens. It becomes so weak that it cannot support the clip anymore, and the clip sinks towards the bottom. Here it is. Now, what happens when we actually create a soap bubbles? Here we have an enlargement of a soap bubble. The bubble itself is constituted by a thin film, and this thin film has two surfaces and the bulk in the center. We can think of it a little bit as a sandwich. The two soap surfaces are the bread, and the bulk in the center is the filling. We already know that on the surface, the soap will tend to stick the heads in and the tails out, and this reduces the surface tension. In the bulk, the soap will tend to create configurations like this. These are called micelle, and all the tails stay away from water at the center of this configuration, and all the heads point towards the water itself. Since the soap weakens the skin of the water, it gives it enough elasticity to be able to blow the bubble itself. By the way, this drawing is clearly out of scale. Indeed, the real size of the molecules is 100 times to 1,000 times smaller than the thickness of the film itself. And the film is less than a millionth time thinner than a human hair. It's really tiny. Molecules like soap are called surfactants, and they all have this characteristic of having one part that is attracted by the water and the other that is afraid of water and wants to stay away. Surfactants play a really important role in life. Let's give a look here at your lungs. The last part of the respiratory tree is composed by alveoli. The alveoli, here you can see a bigger image, they are like little balloons. They inflate and deflate, and they are the main place where the exchange of oxygen and CO2 in the blood takes place. So they're really important. The walls of the alveoli is covered with a surfactant. This surfactant can reduce and vary the surface tension of the alveoli themselves. And this is what allows the alveoli to inflate when we breathe. In case of some sicknesses or when there are some premature born babies, it can happen that there isn't enough of this surfactant on the wall of the alveoli, and as a consequence, the lungs tend to collapse. They cannot be really inflated, and this makes respiration really difficult. Now that you know what the surface tension is, you can try to cut out some paper models of a boat, something like this, and find a way to power them using your knowledge about surface tension. See you soon! So that was easy. It was too easy, maybe. You just had to put a little bit of soap on one side of the boat, and actually the boat was pulled towards the other side. This is because the soap is reducing the surface tension. There it is. Now we are ready to understand what is going on at the space station. In the space station, we are in a situation of microgravity. The electric forces are the same, which means that the attraction between molecules is the same and the surface tension is the same as on Earth. What is different? Let's consider this circular frame and imagine to be here on Earth and to create a film of water. Then what happens is that a little amount of water will drop in the center of the ring. The film sags a little bit, and the water starts to drain from the edge toward the center. This makes the center of the film heavier and heavier, and it will create kind of a little pool. At some point, the surface tension cannot win gravity anymore, and the weight of the water will make the film break. In the competition between gravity and surface tension, gravity wins. What is different at the space station? As you have seen, the astronaut was able to create a film that was really stable, thick, and it could last up to 12 hours. This is what he noted. Well, the difference is that the film there is weightless. Being weightless, the surface tension doesn't have anything to fight against. It holds the water together, all the molecules can stick together, and there is nothing that tries to break it, pulling it towards the bottom. This is it for now. In the next section, we will investigate the shapes of soap bubbles. Welcome back. Now we're going to find what is the energy of a soap film and how it is related to its area. In order to do that, we're going to use a metal frame with 3 sides that are fixed and 1 side that is that can slide. One side that can slide. Let's give a look here at this sketch of the frame. So here we have 3 sides that are fixed, 1 side that can move, and this side is long L, let's say, and we try to create a film in the middle, applying a given force, F. This sounds more complicated than it really is, because what you're going to do in practice is just to take this frame and dip it in soap water. Then we pull the 2 sides apart and in between them there is a thin soap film. We will see it better soon. Let's first write down what are the important equations here. When we create a film, we actually apply a force. This force is related to the surface tension. The first surface tension is indicated by the Greek letter gamma, and it's equal to the force that we apply, which is parallel to the film, divided by the total length of the film itself. You remember that a soap film, it's actually a sandwich of 2 soap layers and water in the middle. So we don't have just 1 surface, but 2. Here is the second one. And this is its length. So when we apply the force, we apply it to 2 surfaces. This means that the total length will be the sum of the 2 lengths of 2 different surfaces. Capital L is equal to twice the side of the film, little l. So the force, which acts in this direction, parallel to the surface, it's equal to the surface tension gamma times 2 times little l. When we apply a force to move an object, what we are doing is we do some work. And this mechanical work is equal to the force times the displacement. In our case, we moved the side that could slide over a distance x. So x is our displacement. Let's substitute the force And we will get that the work is equal to gamma times 2 times L times X. But L times X is the area of the film. So the work is equal to gamma times 2 times the area. Gamma is constant for constant temperature and in equilibrium conditions. So we end up with a relationship between the work that we apply to make a film and the area of the film itself. They're proportional. This work is actually the energy that is stored by the film, and it's available to the film itself to do something else. Let's go back to our frame. We can look at it closer. Now here there is no film, there is nothing. You see, these are the sides that cannot move, and this one can slide. If I put here this side and I let go, nothing happens. Well, because there are no forces involved. Now I'm going to create a film. I take this frame and I dip it in the soapy solution so that I have a film, a soapy film in the frame. Here it is. Now when I let go, you see that the energy that was available has been used to pull back the film. This is the surface tension at work. Now I would like you to use a similar frame to try to measure the surface tension of different soapy solutions. See you soon. Nature works in the greatest possible economy. Or we can say nature is relaxed. This statement was first introduced by the Frenchman Maupertuis, and then it was studied in different contexts by a series of mathematicians, such as Leibniz, Euler, Fermat. Nowadays, it's widely used in physics and it's well understood. It's known as the least action principle. In simple words, we can say that nature will tend towards configurations of minimum energy. Here I have a ball and two ping pong balls, one at the bottom and the other one on the edge. Which one has the higher potential energy? You can discuss it and then see you back. I am sure that you got the right answer. The ball at the edge has a higher potential energy than the ball at the bottom, simply because it's in a higher position. Now what happens if I perturb it? It's easy to forecast. After a few oscillations, both balls end up at the bottom of the ball, simply because nature is making them evolving towards the situation of minimum energy. So this is true for a mechanical system. This is true for soap bubbles. We already know that in the case of soap bubbles, the energy of the soap bubble is related to the area of the soap bubbles. So if nature wants to minimize the energy, it seems that it also wants to minimize the area. Is this really true? We're going to verify it using a metal frame. I need an assistant. Walter, could you please help me?
I will be happy to help you. Where do you want me?
Please come here. I'm
Very
going
good.
to dip this frame in soapy water so that we can create a film.
And that's what you want me to do, or you will do that?
I can do this.
Okay.
I want you to take the needle and be ready.
Oh, so I have the easy job.
Yeah. So let's see now. I'm going to put...
I'll try it with the other side of the pin.
Yes.
Ah, it worked beautifully. I did it with the other side of the pin.
Yeah.
This worked very well.
Nice.
I think you got it now.
Yeah. So Walter, it finally worked. It was a bit tricky, but we managed to do it.
I'm not sure that people will be able to reproduce this, by the way. It's not an easy experiment.
With a lot of patience, they will manage.
With a lot of patience, yes.
So, try to do this now in the classroom and see you in a while. Welcome back. So I hope that you managed to create your little circle with the thread. Do you know why that happened? Well, you should know that once you take a given perimeter, the two-dimensional figure that encloses the maximum area is the circle. So when we make the film pop in the center of the thread, the film wants to minimize its area because this is what naturally it wants to do, minimize the energy. In order to do that, the hole has to take the maximum possible area. This maximum area is the circle. The circle, the hole is bigger, then all the film around it is smaller. Problem solved. Actually, this is really fun, but it has also some practical applications. You can give a look here at this sketch on the computer. There is a problem that is known as the motorway problem, or also as Steiner-Fermat-Torricelli-Cavalieri problem, from the name of the scientist who first introduced it. This problem is concerned to find the answer to these questions. If you have different points on a plane, what is the shortest path that connects all of them? You can think of each point as a city, and the path can be a motorway. That's why we call it the motorway problem. I'm not going to explain this in detail right now. You will see it in the activity paper, how to proceed. Essentially, you will have two plates parallel to each other. You will put some pins, one for each point, for each city. You will dip this in a soapy solution, and the soap film will find the best configuration that connects all the pins. This is a really complex mathematical problem, but with soap bubbles, you can solve it really easily. So if you want to try this activity, you can stop here. If you want to continue, stay tuned, because now we are moving to other surfaces. We all know soap bubbles. Soap bubbles are spherical, but why? In principle, if we take some air, it can have any possible shape. We can have soap bubbles, you can see the image here, we can have soap bubbles of any shape you can imagine. However, this is not happening. Well, right now, you know enough to imagine that this has to do with the area, with the energy of the soap film itself. Indeed, what happens is that for a fixed volume, the two-dimensional surface that minimizes the area is a sphere. So this is not a big surprise. It's quite difficult to demonstrate it mathematically. I'm sure that you will be able to do it once you learn a little bit of calculus, but for now you can just get it from the intuition of soap bubbles. We blow in a given amount of air. In order to enclose it, we have to find the shape that minimizes the area, and this is a sphere. Now, a sphere will form because we don't have any other constraint. But we can try to create bubbles that are different from a sphere. Let's see here, for example, I have a kid's pool and a hula hoop. So essentially, I have two rings. Can you imagine what is the shape of the film that will be formed once I pull the hula hoop here? Here we have a kiddie pool with some soapy solution inside and the hula hoop. So we have essentially two rings. We want to know what happens when I dip the hula hoop in the soapy solution and then I pull it up. Before I pull up the ring, stop the video and discuss in the classroom what shape you expect. I will see you in a couple of minutes. Okay. Here it is. It's not a cylinder, it's a catenoid. It's bent in the center. Et voila! Here we are. This surface is called a catenoid. A catenoid is the surface that you obtain when you revolve a line that's called the catenary. Well, this is a catenary. It's the shape taken by a chain when it's free to hang out, and all the forces are uniformly distributed. A catenary is very common in nature. You can see, for example, here, this image of this nice mammal called the sloth that is hanging from a branch, and its spine actually makes a catenary. Catenary is also used in architecture. This is because, again, it minimizes the energy. It's very stable. Inverted catenary make very nice arches. And here you have, for example, the Gateway Arch in St. Louis. Maybe you were surprised to see that when I pulled the hula hoop, we obtained something that was different from a cylinder. I was expecting a cylinder myself. We can explain this a little bit intuitively. Let's give a look at this glass. This is a cylinder. If I want to cover it with stripes of paper, I have to take stripes that all have the same length. So here is one. Here's the second one. And so on. Here I have stripes all of the same length. However, a catenoid is thinner in the center. So if I want to cover a catenoid with stripes of paper, I will start from stripes of the same length here, but then I will need stripes that are shorter and shorter. This explains a little bit why, when we have two rings, the surface in between is not a cylinder, but it is a catenoid. The catenoid has a lower surface area. Again, you can make a precise mathematical demonstration, but to do that, you need a little bit more math. So maybe you have to wait a few years. That's it for now. See you soon. Hello again. Now we know almost everything about the shape of soap bubbles. And we know that soap bubbles are actually useful to study surfaces with a minimum area. And in principle, they're good physical models to try to create communication system. I hope you tried the motorway problem. However, soap bubbles are useful also in different contexts. For example, in architecture. You can see one example here. Here we have a frame that has a spiral shape, and once we dip it in a soapy solution, the soap film takes a very characteristic shape, a surface whose name is helicoid. The helicoid has been used for centuries in architecture to create winding stairs. And here we have an example. This is the stair located at the Vatican. There is a famous German architect named Fray Otto who created really beautiful and daring structures with soap bubbles. You can see here an example. This is the roof of the Olympic Stadium in Munich, in Germany. And here there is another building by the same architect, and you can have an idea of how he used the soap bubbles to create it. On the top left of the image, there is a soap model. Here we have the wires that he actually used to create the model. He then dipped the model in a soapy solution, took it out, and saw how the soap film would configure, what shape would the soap film take. This was tested because, of course, it has to be stable not to break when there is wind, when there are all kinds of perturbations. And then the architect was projecting this model making a real design. And here on the top right, there is the network of the building. Here it is. And at the end, we have the final building. Soap films minimize the energy. We already know this. And so it's really convenient to try to create some buildings that mimic them, that are following the same shape. Finally, soap bubbles have been used in biology as a good model for membranes and for the partition of cells. On the left here, you have an image of the wings of a dragonfly, and on the right, there is a model of these wings. This model was created using just a frame and soap bubbles, and you can see that it mimics pretty well the wings of the dragonfly itself. And we will finish with frog eggs. Frog eggs form in a solution which is clearly different from a soap solution or from water. However, the shape is really similar to that soap taken by a soap foam or by the water bubbles. In this image, on the top, you can see frog eggs. Here on the left, there is a soap foam, and on the right, there is an image from the video that was taken at the International Space Station when the astronaut was actually putting Alka-Seltzer inside the film of water, and this was creating bubbles. These bubbles will compete and will divide and interact all in the same way. That's it for today. There are many more applications of soap bubbles in physics of turbulence, in astrophysics, in chemistry, in material science. And I hope that you will continue to explore the world of soap bubble because there is a lot of fun. We just barely touched the surface. In the next module, we will discover where the colors of soap bubbles come from. Goodbye for now. Ciao! Hello, teacher. So this model is designed to explore the science of soap bubbles. We first start with the concept of surface tension. If you want to talk a little bit more about it, you can maybe expand talking about intramolecular forces. In the next segment, we make a connection between the energy and the area of the soap film. And this gives the possibility to talk more about mechanical work and energy. And it gives the possibility to understand something about the geometry of soap bubbles without entering into too many mathematical details. Finally, we are just studying some applications of soap bubbles, mainly in architecture and in biology. Once you make your soap solution, you can try to actually change the proportion from the basic recipe that's written in the teacher guide. This is because the proportions change depending on the weather, depending on the water, depending on the soap itself that you're using. So you should really try to experiment. It can be a little bit frustrating because every time that we try to make a demonstration, we had to repeat it many times. But once it works, it's really rewarding. So I suggest to be patient and try to do it until it works. To make the frames, I was using a copper ring. You can use any metal, any wire that you can deform. And you can also try to create different frames. There are some examples on the book by Charles Boyce that's listed in the references. And finally, now Walter and I will show you how to make a catenoid in your classroom. You can see it in detail. Have fun. Goodbye. So now Walter and I are going to show you how to make your own catenoid without needing a kiddie pool and a hula hoop, but just with two circular frames.
All right,
So,
if you're ready, I'm ready.
okay. Yeah, if you can take a needle, and then here I'm dipping the frames in a soapy solution. And bring it to the camera here. Now I pull the two rings apart, and you will want to pop the circle in the middle.
Just try to hold it.
Yeah.
Yeah, you got it.
There it is.
Yeah, you got it. You have the, yeah.
You can see now that in between the two rings,
Very nice.
there is a surface. That's the catenoid.
And it's completely open here.
Yes.
You can completely go through here, and I popped them.
Ah, it's okay.